All right. Thanks again, everyone, for being here. So this presentation is based on a paper that I wrote with Scott Martins from Tech. It was published at the last Things and Mind Use Conference in Denver last November. So the focus of this presentation is on tailings and mine waste facilities because that's mostly my background. But some of this discussion is valid for other things as well. Okay, credible failure modes. It is a core requirement of GISTM. Which I understand here in Australia is actually GISTM. But I'm pretty used to saying GISTM because it's mostly what everybody else in the world is using, so you'll forgive me for keeping on saying GISTM. It is a core requirement for a number of things, but the main objective is to minimize risk for credible failure modes. It's used for all those things in GISTM, and it has led to significant debates and lack of consensus around the definition of what is a credible failure mode and what is the criteria for calling something non-credible. The concept is actually relatively simple. It's to ensure that all potential failure modes are considered in a risk assessment. And you create a list of credible failure modes that's comprehensive, so all risk is managed with sufficient rigor to a negligible probability of failure. And that's where the confusion starts, what's negligible probability of failure. So in any case, for failures that are declared to be non-credible, you need to have like a good degree of confidence that is not credible. So you need to meet a really high bar so that we're not taking on more risk than we intended to because we said that something is non-credible and in fact that's not the case. Two important concepts just to get us started. It is important to realize that we can have a safe structure that has many credible failure modes. And also that there is a minimal correlation, oops, that went too fast, a minimal correlation between the number of credible failure modes and safety. And this is pretty evident from commercial aviation, which being learning from past failures, and the adoption of a safety culture has resulted in very high levels of safety, despite the fact that there are hundreds, if not thousands, of credible failure modes for each kind of aircraft. So if we were to take a commercial flight and apply the ICODE 2019 consequence classification that was adopted in GISTM, we would say that each and every commercial flight would classify as having an extreme consequence of failure. So here how they've been managing safety. They had many tragic accidents, but what they did to improve safety is really remarkable. So if you take a look at this graph of the number of fatal accidents per million commercial flights on the vertical axis and on the horizontal axis, the data goes from 1970 to basically 2021. We added an extra point there for 2023. You can see that they managed to reduce the number of fatal commercial flights from 6 per million to, in 2023, basically 0.03 per million, which is basically 3 times 10 to the minus 8. So that's an extremely low probability. But even if we look at the 5-year average, the probability of a fatal commercial flight is 10 to the minus 7. So pretty impressive numbers. Now, it is plain to everyone that unfortunately the safety record of tailings dams has not met expectations, either of the mining companies or the regulators, or certainly not of the people that are affected and exposed by the risk. So there will always be hazards associated with mining. We're not fooling ourselves here. But just as much as there is always hazards associated with flying. So let's dig in, with that context, let's dig in into the definition of credible failure modes for the GISTM. I'm sure everybody here is pretty familiar with this definition, but I do want to highlight the last phrase that's in bold, that says the term credible failure mode is not associated with a probability of this event occurring, and having credible failure modes is not a reflection of the facility safety. And I'm highlighting this phrase because that was the one that was subjected to the most discussion and most confusion, different interpretations. So the intent of this sentence in this definition here is just to acknowledge that a credible failure mode is not, we're not making any statement about how low or how high the probability of failure is. The probability of failure is purely related to how that failure mode is managed. So you can manage the credible failure modes to have a very low probability of failure, or you could do nothing and leave it at a relatively high probability of failure. So stating that it is a credible failure mode is not a statement of probability of failure. So now this term credible failure mode wasn't a GISTM invention. FEMA, which is the Federal Emergency Management Agency of the government of the United States, defined credible failure modes in their guidelines back in 2015. So the definition is here similar to the GISTM definition. I just want to flag here that we note that this definition is based on risk, so probability and consequence. So after the GISTM, which is FERC, which is the Federal Energy Regulatory Commission in 2021, also came up with the definition of failure modes. And FERC is United States government, but it's relevant here because it is used in many places, certainly throughout the Americas. But also, it's interesting to note here that they defined credible failure modes on the likelihood of the potential failure mode occurring. And they also went out and proposed a threshold of negligibility. So to say, if a failure mode has an annual frequency of occurrence probability of less than 1 in a million, then it's non-credible, because they proposed, or they stated that when the probability is that low, it's a non-credible failure mode. So 1 in a million, 10 to the minus 6, right? So there is no actually single definition. So FERC is pretty common to be used. But they, some other people propose that, no, it should be 10 to the minus 7. So that's another area of a lot of discussion. Is it 1 in a million? Is it 1 in 10 million? What is the level of probability of failure that we could turn around and say, okay, that's not a non-credible failure mode? Well, if I go to the dictionary, negligible is something that's commonly defined as so small and unimportant as not to be, or to be not worth considering. So we propose that in this case, it's not just about probability, but it is also about consequences. So the FEMA definition, as I flagged, does talk about risk, acknowledging that both probability and consequences. And we could think about it this way. If I could give a real Canadian example here. So if I'm hiking in the Rocky Mountains, and I get my arm scratched on a tree, like, there's a pretty high probability of that happening. But who cares? Like, I'm not going to stop hiking. That's not a credible failure mode. So it has a pretty high probability, but it's negligible. Who cares? Get a scratch, the next day you're good. Now, if I look at the probability of encountering a grizzly bear on that very same hike, the probability is pretty low, but that's not negligible. That could be a credible failure mode on my hike if they're warning that there are active grizzly bears in the area. So when you think of something that simple, you could say, what is negligible is so unimportant as to be not worth considering is not just about probability. So in our world, that little slump on the downstream slope of a dam that's, a few cubic meters, yeah, maybe that happens more than we wanted, but, that's not something to worry about. So we propose that's not about just this probability to define the threshold of negligibility. But also the other thing to think about, if a lot of lives are at risk, well, then maybe 10 to the minus 6 or 10 to the minus 7 is not good enough. And this notion is honored in the alarm concept, so as low as reasonably practicable. So I would imagine most of you are familiar with that concept. It came from the Health Safety Executive in the UK, and it's widely used in risk management for all sorts of things, right? And has been adapted for dam risk management. So in the vertical axis, you have the annual frequency of failure, and then versus the number of lives that you could be at loss. So if we take a look, like 10 to the minus 6 is not in the area where the risk is generally acceptable if you are on the right-hand side where the potential loss of life is pretty high. And in fact, even the 1 in 38 million of the airline industry is not necessarily acceptable either, even though it's 3 times 10 to the minus 8, if you have a lot of people in the line of harm. So, there is a lot to be discussed here. And also the other thing that's important for us to think about in our business. So if you say, well, but I'm going to design my dam to an extreme consequence regardless, well, that's great. It is in the guidelines of many guidelines, GISTM, ENCODE, and others. And then it's telling you to say, I'm going to design for, say, for example, an earthquake with a probability of occurrence of 1 in 10,000. So that's 10 to the minus 4. So that's a long ways from 10 to the minus 6 or 10 to the minus 7. So not only you are going to have to design for that, but also we're going to say, okay, if this event with a probability of occurrence of 10 to the minus 4 occurs, I still need the probability of my structure not failing to be 1% or less to even get to the 10 to the minus 6. Or if you want to talk about 10 to the minus 7, we need to design such that probability of failure is very small. So we need a very robust system. So while you might argue that's not necessary to invoke a specific numerical threshold for negligibility, when we talk about these numbers, you get an idea of the level of robustness that's necessary for our designs to meet a condition of, say, these are non-credible failure modes. It also, back to the analogy of the commercial aviation, they are at 1, like right now, 10 to the minus 7 or 10 to the minus 8, but they're still considering everything a credible failure mode. and they're still working with preventative maintenance and this and checklists and this and the next thing, whatever is meaningful in their business, to reduce the risk of a fatal accident more and more. So, which is very consistent with the concept of ALARP, as low as reasonably practical. So that's a thought for us to keep in mind as we decide those things. So, these probabilities provide a conceptual indication of the threshold of negligibility. However, one thing that's important for us to think about is that humans are very poor at estimating very low probabilities. And we frequently estimate values that are much lower than reality. So Steve Vick has written extensively about this. His book is Degrees of Belief. He's got papers on this. So it's if you're interested in this, it's an interesting read. So for example, an example that Vick gives of NASA, they're widely regarded as one of the most technologically sophisticated organizations in the world. And NASA senior management and senior technocrats, they believe that the probability of failure of a catastrophic loss of a space shuttle was 1 in 100,000. So that's what, 10 to the minus 5. But the reality wasn't 1 in 100,000. The reality was 1 in 68. So 2 catastrophic vehicle losses in 135 hours. So that's humbling to me, because if the NASA brains can be that far off, I feel that we have the humility to think that maybe we're not estimating this right. Also, the other thing for us to think about is particularly difficult to estimate probabilities when we don't have a large population. So if I produce nuts and bolts and I'm producing like millions of those things and I can count how many came out with defects, yeah, statistics is your buddy, but like even for aircrafts and space shuttles, they're man-made things that you could argue they're somewhat comparable to each other. But in our business, how many dams had similar cross-sections, similar foundations, operated similarly, and that had been subjected to the same loading conditions, the same earthquakes, that we put the population together and say, okay, what's the probability of failure? So it's a big challenge in front of us. And even if you talk about, okay, it's probability of an earthquake or a flood, there's enough of those that you could do statistics. But what about slow stability? What about the syntagy-related failures? That's another degree of difficulty, right? So, now with all the difficulties in front of us, how exactly do we go about doing credible failure mode assessment? So I think the first thing that you do, you engage a multidisciplinary team to assess all potential failure modes. So you get people from all technical disciplines, management, designers, EORs, operators, construction personnel, 9 plant people, monitoring team, everybody. Because like the plant people could say, oh, our tables are going to get finer in 2 years from now. Well, that's relevant. What kind of failure mode could that create? The operations people know when it is that they can actually follow certain styles of operation or not. So I've been part of many of these things, and the richness of having everybody around the table is unbelievable, because everyone on this multidisciplinary team can contribute something that someone else in the team didn't know about. So you get this team together and you focus on producing a comprehensive and complete list of all physically possible potential failure modes. So once you get that list done, here's the process. Step 1, you take a look at the failure modes that are clearly not physically possible, who may have still on the list. because at the first part, you don't do a lot of analyzing, you just list. If somebody has a crazy idea, you put it on the list. So step one, there are some that you probably can eliminate without any additional consideration. This is not actually physically possible. Step two, there might be some potential failure modes that may be determined to be non-credible because you already have sufficient data, sufficient evidence, and you can conclude that based on what you already have, that the probability and or the consequences of failure are such that you could say this is clearly negligible. And then step three, you're left with all other potential failure modes that need to be assessed in detail. Maybe you need to do more site investigation, maybe you need to do more laboratory tests, or maybe additional analysis to get to the point where you have to decide which ones already meet the criteria of negligibility, or the ones who have already been managed to an acceptable level of risk, or the ones that still need to be managed to bring it to a good level of risk that's compatible with what you're comfortable with. So in this process of assessment of negligibility, you're going to be asking all sorts of questions. There's a big list here. There's a bigger, longer list in the paper, but these are just examples. Each facility will have its own characteristics and is going to have its own list of questions to ask. I just want to highlight the very last one about human actions. Well, humans are prone to errors and omissions. And we have mechanisms to prevent those. We train people, we have SOPs, standard operating procedures, but we need to stand back and say, if maintaining the integrity of a facility depends on people acting or acting correctly, is this failure mode still not credible? People change, people have bad days and good days, stuff happens. So that's one that it's worthwhile thinking about. Couple of other things to think about. Well, you make your big list of potential failure modes. And you determine the basis for deciding what's non-credible, what's already an acceptable risk level, and all this. And when you do that, you have to think about both primary and secondary failure modes, which is something else that sometimes people forget. So, for example, I may have a facility that you say, oh yeah, we can store an entire PMF, potential maximum, probable maximum flood. So, overtopping is not a credible failure mode. Or maybe I can even store 2 PMFs. But if we have a slump, or if you have enough settlements that in a certain area the crest is a little lower, well, overtopping is not a potential failure mode, but after this other event happens, it can become a potential failure mode. So these primary and secondary failure mechanisms can be a problem. And actually, this is what happened at Vion. So I don't know if you're familiar with Vion, and this is a photo of Vion looking from downstream. So people there knew that the abutments immediately upstream of the dam that you can see on the background of this photo were not stable. So they put an awful lot of efforts into assessing whether those slopes would fail or not, and if it failed, how big a wave it would cause, and what would the wave do over the dam. They did physical models, and they concluded that beyond a doubt, the failure is, if this failure happened, it would overtop the dam, it wouldn't be that big a deal. Well, it didn't turn out to be the case. It created a humongous failure. This is the view of the dam, not from the other side, from the upstream, looking downstream, and you see all the slopes that failed. It created a 250 meter high wave, went over the dam, and 2,000 people lost their lives. So, you know, back to the aviation industry, we need to learn from our mistakes, full reliance on modeling and physical models. Gotta be careful with that. We also need to be to recognize all the uncertainties that we have, insufficient site investigation. Well, maybe we have a lot of site investigation, but could we have like Mount Poly? Could we have a weak zone in between two boreholes that didn't get properly identified? So materials may be mischaracterized, numerical models that don't fully represent soil behavior. Soil is non-linear, very complicated, you all know about that. And the models are the best we can do today, but they are still a simplification. And they have lots of parameters, some of which are not easy to define. There is inherent uncertainties in geotechnical engineering, as Morgenstern pointed out. And not just in geotechnical engineering that we are on a steep learning curve. There are limitations to the current level of knowledge in all sorts of other technical disciplines. So there are a lot of these uncertainties, climate change and other things that we need to acknowledge that when we do these assessments, we are dealing with all these uncertainties. This is not an aircraft that was man-made with steel produced to specs and all that, right? Okay, so what other product do we need out of the critical failure mode assessment? We need detailed documentation. Nobody likes to document. Most engineers that I know, including myself, don't. Super important. Detailed documentation allows us to, first of all, put the process out for independent review, which is a very important portion of risk management. Allows us to demonstrate that we had a thorough process to go through this. But also potential failure modes change with time. Maybe something is not a potential failure mode when the dam is low, but maybe as the dam goes high, it changes. The risk also changes when population downstream changes. So it needs to be redone every so often. So if you have to start from scratch every time, it's time consuming, it's boring, it's expensive, so it's a starting point. But also, you know, it's in the mining industry, facilities change ownership, facilities are put on hold for a while and then they restart, people change, so the new owner or the new team that comes later when a facility is back online, that's a starting point for them. So even if you have a perfect knowledge base, which is a GISTM requirement, and most of us are still working on it, that is a solid document to see what people before had for data, had for credible failure modes, and all that. And not recognizing credible failure modes is the cause of failures in other facilities. Stava in Italy, 1985, killed 286 people. I worked on that project, it was pretty sad. So if you don't know about Stava, this is a little map. So up on top you see the two blue dots at the two Davis facilities. Down the valley you can see the red lines show the path of the failure, debris, water, and everything. And all the little dots, the black dots downstream, is the town of Stava and the houses around it. So the facility was closed for a number of years, I forget how many, and then the regulator said, well, if we reopen this facility, it would create jobs, so gave the facility to some local people who had no idea of the history of the project, had very little documentation. They didn't operate right and ended up with a failure. So documentation is incredibly valuable. And I also listed here that the products of this are the important intangibles. So on my personal experience, when you put that multidisciplinary team and you talk about failure modes and you talk about all the stuff we've been talking about, it creates a little magic in the team. There are people in operations that says, oh, I didn't know if we change the fines content or that's coming out of the mine, it has such an important factor. On the failure of Samarco, I ended up talking about dozer operator that said, I had no idea how important my job was. And my job was boring. I just drove that dozer back and forth the whole time. I had no idea of the importance of creating a dilated field that won't liquefy. You know, I would have done things differently should I know that. So when you put all these people together, not only you share information to find out what are the credible failure modes, you help people understand what's important, what's not important. If something changes, who do I need to talk to? And they know the people that they need to talk to. So in my professional experience, the intangibles are probably one of the best risk management tools that you get, and operating as a system, operating as a whole team. And we don't tend to understand that. Okay, I also have a photo of the two facilities here, the upper and the lower one. All right. A couple of factors that are necessary for good risk management, but they are not sufficient. Designing to meet the regulatory requirements or even the good industry practice, absolutely necessary, but that alone doesn't guarantee sufficiently low risk level. Some of these regulations are necessarily, they're pretty generic. Therefore, all the facilities in that jurisdiction, so they're not necessarily dealing with all your own issues in our own facilities. Designing for extreme loads, like the 1 in 10,000 year return period, we talked about that, not sufficient. Meeting a required fact of safety. Many regulations don't say you have to have a fact of safety 1.3, 1.5, but they don't say anything about which parameters you should use. So it doesn't mean anything. And in my keynote and Tailings and Mine Waste, I talked a lot about that. And maybe a good selection of fact of safety and good selection of parameters for one facility might work really well, but for another, the deformations might be a little too much, and it's not adequate. So that's an important one. Good performance demonstrated by monitoring surveillance. That's pretty important because it allows us to say, calibrate the assumptions we made in the design, the parameters that we adopted, like is this performing the way we assumed it would be performing, and give us an opportunity to say, wait a minute, this isn't doing what I thought. Maybe these parameters that I took from small samples or CPTs here and there, they're not operational over a large area. So the industry is moving more and more towards this performance-based design, which is super important because it allows us to manage all those uncertainties that we were talking about earlier. So very important, necessary, but again, not sufficient. Okay, now we've done this credible failure mode assessment, we did the validity check, or warned for the things that are difficult, we need to do now a validity check. So if we got it right, the conclusion that a particular credible failure mode or a particular failure mode is non-credible, it should logically lead to the absence of any requirement of any control. If you still need any kind of control, it's our clue that this is really not a non-credible failure mode. So that's important to do a little reality check. So we have a redundant system, checks and balances that manages the risk. Okay, so why this is so important? Because if we don't recognize credible failure modes, we're not going to do anything about it. Good design, good oversight, good construction, good monitoring, all of that is going to be seen as unnecessary because we don't have a credible failure mode. So seeing the credible failure mode is super important. So this is the bow tie approach to risk management. I'm pretty sure everybody's familiar with that. On the left-hand side, we have the hazards that exist, whatever that is, poor foundation, earthquake, whatever that is. And then in the center, we have a failure event or an unwanted event of any sort. So between the hazards and the failure modes, then the risk management system has some controls, some barriers. Whatever it is that we put in place to reduce the probability that hazard that exists leads to a failure event. And then on the right-hand side of the bow tie, we have the consequences. So should the failure event occur, despite of the barriers that we put there to lower the probability, then we would have other measures in place that such that should that event occur, we minimize or eliminate the consequences. So that's how the bow tie works, right? So here's an example that also everybody knows, the Titanic. Well, the Titanic was believed to be unsinkable, which was effectively saying that the Titanic had no credible failure modes. So this belief led to risks on both sides of the bow tie. So the captain entered the iceberg field in full speed. But there was no need to slow down. The Titanic had no credible failure modes. But the ship only held lifeboats for 50% of the people on board. No credible failure modes. Why would you worry about that? So the crew were not trained and did not practice emergency deployment of those credible failure modes, of those lifeboats, because there were no credible failure modes. There was no need to do that. So had the owner, the designer, and the captain instead recognized all the failure modes, the credible failure modes, there would have been 0 fatalities instead of the 1,500 or so people who died in this event. Because if the ship had slowed down entering the iceberg field, maybe there would have been no catastrophic failure of its hull. But even if that had occurred, even if it slowed down, the 2.5 hours that passed from hitting the iceberg and the total sinking of the ship would have been enough time to deploy enough lifeboats and save a lot of people. So this, for me, is a huge example. Practical example, different in our area, but a practical example that the belief that there were no credible failure modes was the direct cause of enormous loss of life. So if we were to assess the Titanic today with the rigorous methods that we would apply to Artemis facilities, the result would be completely different. So different than Artemis facility, but it's still a valid analogy for us to think about the importance of recognizing as many potential failure modes as possible, the credible failure modes, and have all the controls in place to minimize the probability and manage the consequences. So we need to acknowledge that there is risk everywhere. Unfortunately, there is a perception among some groups and some individuals that tailings and mine waste facilities should have 0 risk. That's completely inconsistent with the existence of pervasive risk throughout our society. Virtually everything that we do has credible failure modes and has to some hopefully typically small risk of failure. Everything. So also another issue that we've been facing as industry is the mischaracterization of the statement 0 tolerance for human fatality. It's used by many companies and it did make it to the GISTM. That statement does not mean 0 risk. So if we're accepting a small risk of a negative outcome that we do every day when we drive our cars and fly and all this, does not mean that the negative outcome is tolerated. So despite the very low probability of the fate of fatal commercial aviation, as we've been talking about, the industry continues to try to improve their safety records further. And the mining industry must also continually work towards reducing the risk of all potential failure modes towards this goal of zero fatalities and catastrophic events. I'm actually quite optimistic because I see our industry having done a step change, that people are taking things more seriously, looking into risk management in a much better way than we used to. Okay, so once we acknowledge the risk, we need to communicate the risk. So it is very natural to think that potentially affected communities would be comforted by us going there and saying, you don't need to worry about anything because this facility has no credible failure modes. Now, if you dig into the literature of risk communication, you see that the experts in risk communication, they are of the opinion that rather than telling people that there is nothing to worry about, it's generally more reassuring to tell people, to confirm that we do recognize that they are credible failure modes, and we take them seriously and we're continuing to manage them. Many times we're concerned that if we're being transparent about risk, we're going to create concerns or stimulate opposition. But when you read that literature of risk communication, I think we could counter by saying that with what actually creates concern and opposition is failures and not transparency. So we need to build credibility, as we all know and we all here concerned about, is improving our track record in our industry of safe and reliable performance, but also being transparent about it. And here's a case where the analogy of commercial aviation is apt again. It's much more comforting to us to know that there is a large team of well-prepared, well-trained professionals that worry about every detail of safety of aircraft. Then if these very same professionals would come to us as passengers and say, hey, there is no possible way that this aircraft could crash, so you got nothing to worry about. I think that's kind of a feeling that we all relate to. If they said that, we wouldn't sit in airplanes with the same feeling that we all do, right? So here's another quote from the same fellow Sandman that I quoted before. If you tell me not to worry about anything, I will end up worrying about everything. I will worry less once I know that you're worrying for me. So in my case, I really like this quote, and I take this is my job description. My job is to worry about everything. So the people who could be affected by the failure of these facilities, hopefully they don't have to worry about it. Okay, so that's all about credible failure modes, and there is a lot to discuss. So I don't think that the ideas that I'm talking about in this presentation and the paper that Scott and I wrote are the last word on this topic, and I hope it is not. We're flagging a lot of things, but there is a lot of work to do. There is more discussion to be had, there's more development to be had, and hopefully our industry will continue to discuss a lot of that, and we'll see where that goes. I'm going to propose a couple of points that we could see where this would go. So the first thing is the tailings dam safety community probably might reconsider the terms credible and credibility. The qualitative and possibly quite subjective nature of these terms is probably not particularly helpful when we're dealing with the complexity and the difficulty of assessing and quantifying very small probability of occurrence of certain failure modes with the type of structures that we have. So I see us moving on from that kind of terminology. And I see us focusing a little bit more on the assessment of potential failure modes using the ALA framework, where both probability and consequences are considered. And when you think about it, both the GISTM and the good practice guides require that you use ALA for considering these failure modes. So if you just use a single framework, it streamlines the process. Instead of using what are the credible failure modes and then have we reached ALARP, let's streamline the process and dive into ALARP readily. And this ALARP approach has the same level of rigor that we've been talking about for defining thresholds on eligibility and deciding what's credible and not credible. It's got advantages as we've been talking about. So just to wrap up here, risk assessments are a key part of managing a data facility, striving to identify all potential failure modes and appropriately controlling the hazards, so the left side of the bow tie, and minimizing the consequences, the right side of the bow tie, and having effective emergency response plans should a loss occur. So we have enough of lifeboats for everyone and minimize the risk of failure. That's our job. So there's some references here. If you're interested, we'll circulate this presentation. So thank you very much for listening to me and being here.
Thank you so much.